Okay, if you click this course project website and scroll down, okay, you can see it's Abel's 1999 paper, which has a sample and hold circuit. It's been a super popular sample and hold circuit. And I have a printed copy over here. Let's take a look at the schematic real quick. It's IEEE Journal of Solid State Circuits, the top journal in integrated circuit design. There are two top publications. One is IEEE Journal of Solid State Circuits. Another one is called, it's a conference paper, IEEE SSCC. That conference is being held every year in February in San Francisco. It's not changing the location because San Francisco is just next to Silicon Valley. It doesn't make sense to change the location because all the CEOs from like AMD, Intel, they will give a presentation in that conference. $800, I think, if you just register the conference and visit. Publish a paper, difficult. Okay. I don't know. I mean, probably only the super top universities in the US and the PhDs or postdocs are publishing probably 2, 3 as a maximum in their whole life to that conference. Considered excellent already. So challenging. Come back here. That's a schematic. Could you tell which one is NMOS, which one's a PMOS? No. Yeah, these are actually NMOS. NMOS, 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 PMOS. So the arrows on the top is PMOS. So this is an inverter. And it has the input shorted together because it's all that called phi. This is that a Greek letter? Is that in Chinese we just call it phi? Is that phi in here as well? Okay. So they are shorted together, and that's the output of the inverter being shorted to another transmission gate. Pass gate is another NMOS, and that's a PMOS. It passes the signal from here to here, and this is a switch. And you can see it's a VDD connect to the gate, so it's always on. It's always on. However, this NMOS is being controlled. It's being clocked. Okay. That's the analog input. So disregard everything here. For example, if you can keep this gate on, and again, this is the NMOS, okay? So when it's pointing out, so the arrow is pointing out, it's a NMOS, it's pointing into the gate, it's a PMOS, okay? That's how I can tell the difference. So this is a NMOS, and it's definitely not a transmission gate. So transmission gate is not helping, so we don't need a transmission gate in this case. I'm going to show you why in a bit. Okay, so sampling, that's an analog input. And the goal is to sample and hold it. So sample and hold. So eventually you are seeing a signal looks like, not this one, like this. So which line is sample and hold module's output? The right one, right? It samples, hold it, samples, hold it. So if we have a, how do you improve the resolution here? Clock increase, sample. Yeah, high frequency of the clock, right? So just sample it faster, right? So you can have a smaller steps, okay? So that's the goal. Okay, now let's come back to the circuit here. So this is the pass gate. It's almost, if you turn the gate on, it's going to pass the analog voltage to this node. This node is the output of the sample and hold circuit. It has a lot of circuits in here, but this is the final output. Okay. If you have a little capacitor as a load, you can hold the charge in there, and you turn it on. That voltage will pass through the NMOS and arrive the capacitor and charge it up. And then you shut it off. It holds the charge. What's the problem of this circuit? What are the problems you can think of? Seems like you just need the NMOS. Why do you need so many other transistors? Let's just use the NMOS. Actually, I'm not sure how that looks like. You want to try it? You probably cannot tell the difference, you know. Let's take a look at it. Here's the NMOS, all right. So if we don't modify the width and length, it's just using a default value. I don't know what that is, but it works. We don't have to modify anything now. And now I'm giving two voltages. One is the analog input. Sorry. One is analog input. One is clock, a switch. They both need to be grounded. So the first one, we name it as V in, for example. And let's create a sine wave. For example, we're using sine wave. Sine wave DC offset should be sine wave. Let's put a 2.5 there, okay, 2.5. And amplitude, let's use 100 millivolts. And frequency, let's use 1K. And don't touch anything else over here. And this is a clock. Let's name it as clock. And I put it here. And it should be a pulse. So sine wave is 1K hertz. So do you want your clock to be faster or slower than 1K? Faster, so you're sampling, right? You're sampling, so you need to be faster. So let's make it probably 20 times faster so we can see the stairs. So initially 0, V on is 5 volts. Delay, let's don't delay it. Just put a 0 here. And T rise 1 pico, T full 1 pico, T on. Since we want to make it faster, so 1K hertz is 1 millisecond for the period. I want to make it 10 times faster. We need 100 micro for the period, right? So it's going to be 50 micro for the on time. And we are going to connect this one here. And because of NMOS, so we don't need a VDD for the well connection. It's just grounded. And V in will be this guy. And I will have a wire here. And I'm going to name it as V out. And let's use a capacitor to hold the charge. So it samples sampled voltage and it's going to hold it there as well. Let's use a 100 picofarad cap. Okay, and I'm going to save it in the folder that has a model file in there. For example, this one. I'll save it as Cascade sampler. And I'm going to run it. Oh, I haven't included the C5 models.txt. Let's do a transient analysis for 2 sine wave periods, or 3 probably. It's going to be 3 milliseconds. Let's run it. Stop time. Not trans, just trend, right? Okay. V in, V out. It works to some extent, right? So the problem is this tech, just to use a pass gate has a lot of issues. The reason is if you are using a small voltage, it's okay. So let's change it. I'm not sure if you can really visualize it, but let's change it and see what's going to happen. So if we move, just increase the voltage amplitude to, for example, 2 volts. 2 volts. So it's oscillating from 0.5 volts to 4.5, still within that 5 volts range. So it reaches a limit. So this part is because the NMOS is not good at passing ones, right? When it's getting closer to 5 volts, it's just getting cut on the top. But you can see at the bottom here, it's also not working really well. If you look at the, it's not tracking it really well. Okay, I couldn't visualize it. So what's happening is, because it's changing the resistance whenever, so the clock is oscillating from 0 to 5 volts, but your VE is also changing, right? So what's happening is your VGS is changing. So if VGS changes, the current runs through the channel will change. And also the channel resistance will change. So the problem is it's creating distortion or nonlinearity because of the VGS change, the change of the VGS over time. So one quick question, okay? Why VGS changes over time? Yeah, why? Yeah, remember when we calculate the VD minus VT trend? So we are considering the clock is on, so the clock is always VDD when it's on, right? Okay. So VDD is a count. So VG is a constant, right? I'm saying VGS is changing, but VG is a constant. What's happening here? The source is changing. Why the source is changing? No, the other side. It's a sine wave. It's an analog input. You couldn't argue. You couldn't blame that one. It's a signal. You're sampling that varying signal. It's an analog varying continuous signal. So you cannot just keep it constant, right? It's changing. So if that one's changing, your VGS is changing. If VGS is changing, you are having a nonlinear activity of the I and resistance curve. Or we can say the channel resistance is going to change, which is going to cause it's called distortion. I cannot show you here. You probably cannot visualize it, but it's just reducing the accuracy of the ADC's result. So the goal is to create a constant VGS, and you are thinking why and how? Because the signal in or the voltage in is always varying and it's unpredictable. It's just the analog input. How can you predict it? How do you know how that changes, right? For example, we can duplicate it to somewhere, right? How can you make a constant VGS? For example, let's make VGS to be VDD all the time. Is that possible? And how? Let's don't say how, but For example, you can make it happen, right? So what would you like to do to make a constant VGS? No. Given that VGS is going to give you a linear output or more accurate output, filtering is not going to work. Filter where, you think? V-in. So V-in is a analog input. It carries information. If you are filtering out, you only want to eliminate the noise instead of decrease. Charge pump. Charge pump to do what? Mm-hmm. But VGS is still changing, right? Since V-in is changing. Mm-hmm. Since clock is just the VDD, we are not considering when clock is off. It's not working, right? So we only consider when VDD is on, when clock is on. So when clock is on, what is the voltage at clock? If clock is on, what is the voltage? Yeah, 5 or VDD, right? Okay, it's a constant. So V-in comes in. If we can add V-in to VDD in some way, VG becomes VDD plus V-in. V-in can change, I don't care. It's just whatever V-in is. And we add it to VG or to VDD and apply it to the gate. Then the gate voltage becomes VDD plus V-in. Does that make sense? Don't worry about how we do it, just assuming we can do it. Here, we make it VDD plus V-in, and here's V-in. What is VGS? What is that? It's a constant. So now the task is to add or superimpose V-in. It's a sine wave or whatever signal. We superimpose it to the gate voltage. Then we can get a constant VGS. So we're keeping the channel resistance a constant. It's not distorting the signal. But intuitively, if you're analyzing the distortion, why it has a distortion. If the channel resistance changes with a different VGS. So for example, the channel resistance is a function of the VGS, right? Mm-hmm. How do we understand it? For example, you get a capacitive load. It can be anything in the circuit. There must be a capacitive load in there, right? So if the resistance change, what's going to happen? Remember, time delay, or TD, is? Yeah. If R changes, the delay will change. So if delay changes, so V-in, so you got a sine wave, there are just multiple points in the sine wave. If you have the same delay, you are shifting all the signal. For example, you got a sine wave like that. If every single point with a different voltage, you are having a consistent VGS. So it's the same time delay. So this point will delay that much, and this will delay that much, right? So you are able to get the same signal as the output, even though it's getting delay, which is fine. But whenever you have a different voltage, it has a different delay, what's going to happen? The signal won't look like a sine wave anymore. This point delays this much, this point doesn't delay that much, is what's here, right? Does that make sense? The channel resistance will change if you have a different VGS. That's why you want to change VGS. One of the reasons is you have a different time delay for every single point or different voltage in the input voltage. Then the output signal will get distorted. It's called distortion. Okay, so now the goal is to keep a consistent VGS. And the way to do that is to add V in to VG. Okay, so you can cancel out V in. So VGS equals to VDD. So now the goal is to create to apply or to add this one to VG to make it happen. That's why in the circuit here, whatever the circuit does is to add V in, to where? Is to add V in to where? To here. Okay. So charge pump is just a voltage booster, pretty simple. It's just boosting the voltage to a voltage higher than VDD. It could be 2 times VDD, it could be 2 times VDD minus VTHN, could be 1 times VDD minus VTH, doesn't matter. So the goal is to boost the voltage. So here the voltage is getting boosted by the charge pump, and most of the capacitor is getting boosted. So you are getting higher voltage here. So the voltage value here will be VDD minus VTHN or 2 VDD minus VTHN. But no matter what the voltage is over here, it's gonna pass the entire VDD to this point. Does that make sense? So if you don't have a higher voltage here, for example, the highest voltage you have in the circuit is VDD for the gate. What is the highest value you can get here? Y2. It's just a 1 most. Right? Yep. If you have a higher voltage, you have the potential to pass the entire VDD to this point. Okay? So this is just acting as a switch. It turns it on and turns it off. So when it turns it on, so when this is on, it turns on this, it's shorting this node to ground. So what that does is it's going to pull charges from this plate to ground. So when it pulls, it's a varying signal, it's an AC signal. So when it pulls, it's going to pull current from here as well to the top plate. Okay, so when this one pulls, it draws current from here to here. Then this one will start charging up the top plate of the cap to 1 time VDD. Okay, so when this is on, right, it's going to pull current from the bottom plate and will create a AC signal because it's changing. It starts pulling. Okay, so that AC will be passed to the other side, so it's going to pull charge to here as well. So it's actually drawing current to the plate and to the ground from the bottom plate. Okay, so after the charge, because this plate is grounded and the top plate is shorted to VDD when this is on. So, and in the second phase or stage, this will be you turn off this NMOS. So you just disconnect this one from ground, and you are having a floating capacitor here. Do you agree with that? It's like you turn it on, you pull it, charge it up, and then shut it off. So what's going to happen? So the capacitor is going to store finite amount of charges into the plate, hold it there. Do you agree with that? It's like you charge it up and disconnect it. Just going to hold the charge in there. So what's the voltage difference between the two plates after that pooling activity? So you don't worry about the phase right now. So I've turned it on, for example, at some point, and this is also on because this is a higher voltage than VDD. I'm going to pull current from here. It's going to dump current to the top plate of the capacitor, and this transistor will pull current from this bottom plate. So actually, it's the AC voltage. It's going to run the AC voltage or current, doesn't matter. It's just the same thing. So it's going to pull energy or power or charges from VDD to here. It's going to charge it up. So it's going to, you are not able to have a higher voltage than VDD at here because this is the whole thing you have. The power supply has a VDD here. So when we turn it on, it's going to start charging up the top plate, and the final voltage out here will be what? What's the voltage here after it charges up the top plate of the cap? After it's pulling the bottom and charging up the top. What's the final voltage here? You have a higher voltage here now. Higher voltage than VDD. Yeah, is that still a problem here to understand? If you have VDD, the highest voltage you can have at the source is going to be VDD minus VTHN. Okay. For the NMOS, if you increase this voltage, and you will, but this is not being changed because they are not in the power supply, and you will be able to pass the entire VDD to here, as long as this voltage is larger than VDD plus VTHN, right? Because that's the gate voltage, that's the source voltage, and gate minus source becomes VDD. No, becomes VTHN. You just need a VGS larger than or equal to VTHN to open it up. Okay, so if the gate voltage is higher than VDD, you will be able to pass the entire VDD to this point. Now come back here. Because this voltage here is being boosted by the charge pump, so this voltage is higher than VDD, so you are able to pass the entire VDD to this point. That makes sense? Okay. So this is during the phase that I'm charging up the cap. Because this is a clock, right? So the DC voltage is a clock, and I can, so at in the second half of the period, it's going to shut this off. Okay, it doesn't matter here. What's happening here doesn't matter anymore. Okay, it's going to shut it off. It's going to be a floating capacitor. The capacitor will be floating there and store a charge, and it's a finite amount of charges being that was came from the VDD in the last period. So what is the voltage across the capacitor after I shut this off? What's the voltage here? Yeah, it's holds VDD. Okay, you're having a VDD here, a floating VDD. What's the difference between a floating VDD and an entire VDD, a power source VDD? What's the difference? So the floating VDD, has finite amount of charges. Is that correct? So if you discharge it, the voltage is going to start dropping, right? But voltage source, VDD, you discharge it, still VDD. Does that make sense? Okay, so this is like a bucket, and this is like a power plant. Okay, the bucket, you drain power from it, drain charges from it, it will be gone. Okay, but we are not consuming a lot of power here, so it's just holding a voltage difference across the capacitor, and you can find out why it's important. Okay, so this is a PMOS, and this PMOS is just used to pass this voltage to here. Okay. So don't worry about the logic here. Okay, for now. So for example, I can turn this PMOS on at some point. I'm going to turn it on at some point. Why I can turn it on? Because this clock will short this pin to ground at some point. So it's going to have a ground over here. Or you can, whenever this is a floating VDD, and if this NMOS is on, so this potential will be added. So this is just a switch. This is on, right? See? It's being added to VSG. Okay? VDD is being added to VSG. Can you see that? If this is on, this is on. or maybe through this voltage. Yeah, through here probably. Okay, so the PMOS is on, right? The PMOS is good at passing VDDs. So VDD from here will be passed to here. And this is directly shorted to the gate of the sampler. And if this is also on, because this is the VDD and this is NMOS, so this is also on, so the potential here will be passed to here as well. So it's basically, these are just the switches controls this guy and this guy. And the thing is, it's trying to add this floating VDD to here. So it's trying to pass the floating VDD to here. Why do we want to do that? It makes sense we need a VDD for the gate because we need to turn it on. Okay. But why we need a floating VDD across the cap to be added to these 2 points? What is these 2 points? See, here's the same node as the gate and the source. So basically, we are adding a floating okay, disregard everything in the other circuits. So we are adding a floating VDD to the gate and source. And this is a VIN, analog VIN. So what happens if we do that? A VDD voltage difference across G and S looks great because this is VGS is larger than VTHN, or this is just a logic 1. This is what we want. However, remember, we need this voltage to be, in order to eliminate the distortion. So now this is VIN. So VIN is plus minus compared to ground. Okay, you got a plus minus. This is one battery. And it's shorted to another battery here. Plus minus, it's the second battery. The 2 batteries are in series. What is the voltage at the gate? Yeah. Compared to the ground. Okay. Is this pin grounded or not? You got a VDD across the cap. Is this pin grounded? Is this pin grounded? If you got a VDD here, it's a floating VDD. I already told you it's a floating VDD. Floating VDD. It's not grounded. It's a floating VDD. Is this pin grounded? No. If this is grounded, we just short these 2, right? You're not getting a series circuit. It's not grounded. It's a floating VDD. That's why we need a floating VDD, so we can add something to it. Is this VIN grounded? Yes. Your input voltage is grounded. Whatever, it can be a sensor, it can be the output of the DAC, can be anything, okay? Whatever device you put on a circuit, you need to ground it. You need to have a common ground. Okay? So you can dig into the details of the logic here and see when these are turned on and it's going to add this voltage to it. But that's the main idea running behind the scene. We just want to add, keep in mind for this, a lot of times I call it Abel's sample and hold circuit, or it's called a bootstrap circuit. And I'm going to show you why it's called bootstrap circuit, because it's like putting a strap in between G and S. It's just forcing these two to swing around, so that around VDD. So it's adding a VDD to it. So these two, this floating VDD across the cap is being used as a strap forcing these to change at the same time. However, this circuit, the main idea of this circuit is very simple. If I'm asking you, what is this circuit doing here? Can you give me a really short answer, just to the key point of it? What is this one doing here? Yes, and how? Increasing the gate source voltage is not accurate. Could you change the wording there a little bit? To how much? Yeah. Or you can say it's superimposing or it's adding a floating VDD to the sampling voltage, to the input voltage. Okay, as a VGS or as a VG. Okay, it's basically adding a floating VDD and a VIN to VG. Okay, how do we do that? We have to create a floating VDD first. How do we create a floating VDD? You have to use a charge pump to increase the voltage. So you're thinking, I was just having a question right now. I know I can probably find the answer really quickly, but why we are not using a PMOS? So the PMOS is good at passing zeros, passing ones, right? If you use the PMOS, it would just pass the VDD over here, right? Why we are not doing that? Why don't they just directly use the PMOS and turn it on and off to pass the entire VDD here? What's the problem? Yeah, get rid of the charge pump, right? Just since PMOS, if you want to turn on the PMOS, just give a zero. It's just no VDD. But isn't PMOS passing the whole VDD? No. For PMOS. I think we can, right? Like that's VDD. You give a zero. Can we get a VDD here? This is VSG, right? It's not changing. Oh. Yeah, you can actually, because the PMOS is good at passing VDDs because it is able to pass the entire VDD over. If you consider this is S, if you consider this is S, then this is G, still VSG, still larger than VTHP. So should be able to. So if you replace this one with the PMOS, seems like it's going to work. I don't know the issues with it, but we can look into that later. So the goal is just to put a VDD here, right? And if you can do it with the PMOS, why not? So that's just a side note, though. I mean, this one has been working. If you want to try PMOS in your circuit, go ahead and do it and see if there's any difference. So what are these ones doing? So this NMOS is always on. Okay. Why do you have a switch that is always on in the circuit? So in the paper, it said this is just providing an extra protection. So when the voltage here could be directly shorted to VDD, and you just don't want to directly short it to ground, it's drawing too much current. It's just adding one more NMOS here. So in that case, why do we still need this one to be indirectly connected to ground though? Why? Why do we still need an NMOS, two NMOSes, right? So this NMOS is always on, but this NMOS is being clocked. So why do we need these two and short it to ground? What is this one doing? So this node is a gate voltage, okay? And why do we need two transistors to short it to ground at some point? So why do we need to cancel that floating VDD? Because floating VDD will be stored here, right? Remember? Will be added here. Why do we need to short it to ground? So if you have a cap, stores the charge. And if you ground the top plate, it's going to discharge it like a bucket. You're pumping water to the ground. You're discharging it. It's resetting VG actually. Why do we need to reset VG? To keep VG a 0. Why? So what's going to happen if you keep VG a 0? If you turn on these two MOSes, you discharge this point to ground, so this one becomes 0, right? Why do we need a 0 for VG? ISO turn on? No, signal is always on. It's a continuous analog input from the sensor. It's like a temperature in the world, right? Can you stop the temperature? How to stop the temperature? It's a continuous analog signal, right? So why do you want to reset this point? What is this circuit doing? What's the name of it? Sample and hold, right? So when you have a VDD here, and if you keep this, if you turn on this one, and have a VDD plus V in here, and you are doing a sample. Why? Because V in here will pass through the transistor and arrive here. If you have a capacitor to hold the charge, so it's going to sample it. Yes. Why 0 is holding? Yeah. So the capacitor here will hold it. Okay. Otherwise, it's tracking. It's not holding. You know, if you keep this on, whatever this one changes, it's going to being transmitted to the output. It's going to track it. So this point will track it instead of hold it. Why do we want to hold it? Why do we need that functionality? What is the something else? But why do we need that? Why do we need it to be held there? If it's changing, it takes time to do the conversion. Remember in the ADC, star ADC algorithm, we run how many cycles? Like 5 cycles for a 4-bit, right? So it takes time to convert it to the final correct output. So it needs to hold it there whenever you have a new the DACs, you have a DA in there, the resist R2R DAC in the ADC, right? So it's converting the voltage, the digital output to analog voltage, and feed it back to your comparator again to compare with the input voltage. Remember? So you need a constant voltage there to finish all the cycles of the SAR logic. If it changes every time you compare with a different value, it doesn't make sense. Okay, so you need to hold it there for a while, so you can run all the cycles. Okay, this one doesn't work. If it works, it's going to be sweet, but it doesn't. So let me show you the sample and hold circuit. We won't be able to do the quiz today, so we'll do it on Monday. Okay. See if I have one. Sample and hold. I don't know which one is correct, but let's just pick up one. Pick up this one. Okay. Double click. You can see the circuit here. So, one question here. Why do I short the PMOS body to source, but not V high? I've told you the PMOS body, like this PMOS, should be shorted to the highest voltage in the circuit, like V high. And you have in your layout in electrical VLSI have been shorting the body of the PMOS to VDD, right? Have been doing that, and the body of the NMOS to ground, right? Remember, I have the two rails, the power rail and ground rail. These are the body contacts. Okay, it's a little P plus and a little N plus. They can short to the highest voltage of the circuit to short the body of the transistor to the highest voltage in the circuit. So why is this PMOS is not shorting this body to V high? Yeah, why? Instead of constant high. So what's the point of shorting the PMOS body to the highest voltage in the circuit? What's the point? Why do we do that? You have to remind yourself about that first. Yeah, stop the diode, right? So you got a PMOS. A PMOS is being built in where? Yeah, unwell. And that's a P sub, right? Okay. And we are so the body of the PMOS is what? What is the body of the PMOS? Unwell. What is the body of the NMOS? P sub. Yeah. Yeah. So the way you short your unwell to whatever the body contact is using a little N plus here, right? So it's highly doped, concentrated, and so has a good conductivity in between the unwell and the metal. Okay, so you short this one to somewhere. Okay, because you don't want to have a forward bias diode here, right? You don't want that to happen. That's a P junction, and you don't want that to happen. So the way to do that is short the body of the PMOS to the highest. That's what you want to do. However, in this circuit, because you are having a charge pump, it's boosting the voltage somewhere. Okay, so the highest voltage in the circuit is not VDD anymore. Do you agree with that? The highest voltage in the circuit is not VDD anymore. Do you agree with that? Sure, you have a bunch of other higher voltages over here. But however, will this voltage higher than VDD? One quick question. What's the voltage across the capacitor? What's the voltage across the capacitor? When it's charging up the cap, it has a floating VDD here, right? So across the capacitor, it's a VDD. However, this sample comes in, okay? So sample voltage, the V in comes in, it's adding to it, okay? So it's gonna bump the voltage at this node to a voltage higher than VDD. It's gonna be VDD plus V in. However, the voltage across the capacitor is not changing, it's still VDD. It's just comparing this node to ground is changing. Why? Because this voltage is higher than VDD. Sure, Obviously, right? Got a VDD plus V in. This voltage is not changing, which is the voltage across the cap. It's not changing. So it's just superimposing this V in, varying V in into VDD. So what's happening is, even though the voltage across the cap is not changing, but the voltage at this node compared to ground is higher than VDD right now. So that's why this point becomes the highest voltage for this PMOS, or for the unwell way. Yeah, for the PMOS. Okay, so if you short, because for this PMOS, the P plus, you got a P plus here and P plus here at the 3N source, right? The P plus. So the P plus will never be higher than VDD plus V. Is that correct? So let's look at this one, the PMOS. Okay, so this is the diode. Okay, this one or this one will be less than VDD plus V in. That's the highest voltage they can have. If I connect the NMOS to the N plus or the unwell, the body of the PMOS to VDD plus V in, am I going to have an issue? Is there going to be a forward biased diode anywhere in this PMOS? Yes or no? Same voltage of the two terminals of the diode. You're getting a current through it or not? No. Is that safe? Yes, it's safe. A lot of times you even need a 0.7 volts to turn it on. There's a threshold voltage, right? But this is the same voltage. Okay. So in that case, it's safe to short the body of the PMOS to where? To where? No, I mean short it to where to make it safe. The body of the PMOS. This is the body of the PMOS. Short it to itself. To a circle there. Short it to where? Short it to where? VDD? Where's VDD plus V in? Gate? Yeah, the source. No, it's symmetric. It doesn't matter. It depends on how you connect it. You can call it drain. I don't think that matters. It's just passing the voltage through. You just look at the VSG, right? On either side, see if you can pass the voltage. You have to analyze each case. It has to satisfy each case. If you assume this is the source, it should work. If you assume this is the source, it should work as well. Okay, doesn't matter which, you have to define which is the source. So I'm just shorting this one to source. I'm considering this as source, but you can say I'm shorting this, the body of the PMOS to G. So in that case, you don't want to draw a common field of pure wire for that single PMOS. It should be in its own wire. You know what I mean? So we draw the dots to cover all the PMOSes. You shouldn't connect the well of that one or overlap the well of that one with other PMOSes. It should be in its own well, because the voltage of that well is higher than others. Make sense? Okay. See you guys on Monday.